Hi everyone, my name is Andre Velasco, and in this video I want to reflect on our final project and on my experience using reinforcement learning during the course. Our project was to make a small two-wheel robot drive through an 8 by 8 maze on its own, from an start position to a goal position, without any human help and doing it completely autonomous. The maze had only 90-degree turns, and to solve it, we used a control system with two layers. In the higher layer, we decided the route where does the robot had to go, and in the lower layer, there was a PI controller, one for each wheel, and it was running on an ESP32 at 200 Hz, and its only job was to follow the speed commands. The robot did not have any onboard sensor to know its position in the maze. That position came from a camera above the maze, which was a zenithal camera, and this part was my main responsibility in the team. For the high layer, we used a reinforcement learning agent, more precisely a tabular Q learning agent with DynaQ planning. We did not program the route by hand, and the agent had to learn it. The interesting part of the work was not only building the agent, but comparing it in a fair way. We compared it against the Mamdani physiologic baseline that we had, and both controllers were tested under the same conditions, the same reference path, the same low-level PI loop, and the same camera setup. Only the high-level controller changed between the two test campaigns. Now, I'm gonna show you uh, about my personal contribution that was the vision system, which is what allowed the RL policy to actually run on the real robot. I worked on the absolute pose estimation because we put an Aruco marker on the top of the robot, and with a homography calibration of the 2.5 by 2.5 meter workspace, the camera gave us the real position and heading 10 times per second. This closed loop this closed loop visual layer was the bridge between the high level decisions and the physical motion. So, what what did I find most valuable about reinforcement learning? First, I liked how the agent discovers the policy by itself from a very simple reward, a small cost per step, a penalty for crossing a wall, and a big reward for reaching the goal. And well, you can see this in the learning curve on screen. At the start, the reward is very low, and then it rises and becomes stable as the agent finds good routes. Second, because the agent is tabular, the policy is fully transparent. Um, you can open the table and see exactly why it takes each decisions. For me, coming from the vision side, it was valuable to connect a clear, readable policy with a clean pose signal, and to see the whole loop work together. There were also real difficulties, and I want to be honest about them. The main challenge was seemed too real. The policy was trained completely offline in a simulation of the known maze, but the professors approved this because the maze is fully known and the state space is small and discrete. But training in simulation forces you to prove that your model is good. From the vision side, this also meant the calibration had to be accurate. If the pose is wrong, the safe execution of the policy breaks. We had to validate that our kinematic model reached an error of only 2.7 centimeters before we trusted it. The clearest physical limitation was a lateral slip of about 8 to 9 centimeters in each in-place 90-degree turn. The camera let us measure this very clearly, run by run, and it was the largest source of error. Uh, Now, the results over 10 physical runs. The RL agent completed 100% of the maze with an RNS path error of 7.07 centimeters in about 71 seconds. And here is the conclusion that made me think the most. The fuzzy controller reached a slightly lower error of 6.14 centimeters, and a Wilk t-test shows that this difference is statistically significant. In other words, RL did not improve the tracking accuracy over Fuzzy, but its advantages were on the other side. It finished the route in about half the time, with a lower maximum error and with much more consistent times. On the next trajectory here, on this trajectory uh, plot, you can see it clearly. The RL runs stay tight and overlapped, while the fuzzy runs reach the goal but oscillate around the path. So the real conclusion is not RL1. It is a clear trade-off, and being able to say that honestly, with a statistical test behind it, was more valuable to me than just claiming my method was the best. And well, to finish, um, what I take from this course is not only that we put an RL agent on real hardware, it is that I learned to judge the feasibility of a solution in a rigorous way and to communicate it with integrity. We also designed safety layers, speed limits, command rejection when the post was invalid, and an emergency stop. A responsible autonomous system has to be safe and auditable before it is fast. For me, that transparency is what separates a nice demo from a real engineering work that you can take responsibility for. Thank you for your attention and thanks for everything over this course.